In the previous sections, we learned about series and parallel capacitors. So let's take what we learned, and let's apply this to a complicated capacitor circuit. So we have our voltage source of 4 volts, and that's attached to a point, and at this point it moves to 2 different wires connected to 2 different capacitors. One is of 3 microfarads, the other is of 3 microfarads also. After the parallel configuration of the capacitors, we move to a series capacitor and then loop back to the voltage source. The series capacitor is of 3 microfarads also. So let's take this one component at a time and let's simplify this down to one capacitor. Step 1, we take 2 parallel capacitors which are attached to the same 2 points, and let's make it one capacitor. From the previous video, we know that 2 capacitors in parallel, or 3 capacitors or 4 capacitors, if they are in parallel, they add together. Since we have a 3 microfarad capacitor and a 3 microfarad capacitor, 3 plus 3 equals 6. So we can simplify these 2 capacitors to one 6 microfarad capacitor. Let's do that now. We have our 4 volt battery connected to our new 6 microfarad capacitor, which is in series with a 3 microfarad capacitor. And how do we know they're in series? Because they are attached exclusively, just them, are attached to the same node or point. From the previous video, we know that 2 capacitors in series, adding the reciprocals to each other, can tell us what the equivalent capacitance is. So let's simplify these 2 capacitors onto one capacitor. 1 over the equivalent capacitance is equal to 1 over 6 microfarads plus 1 over 3 microfarads. And we know that the equivalent capacitance is equal to 2 microfarads. So we can simplify this circuit once again to one capacitor attached to a voltage source. And the capacitor is equal to 2 microfarads with a 4 volt voltage source. If you remember from the previous video, we introduced an equation, and that was Q equals CV. Charge equals capacitance times voltage. We know everything from this system right here except what charges. We know that the equivalent capacitance is equal to 2 microfarads, and we know that the voltage is equal to 4 volts. So let's solve it. Q equal to charge is equal to 2 microfarads times 4 volts. And we know that charge of the system is equal to 8 microcoulombs. Coulombs is a unit for charge. So, what do we know from this? We mentioned in the previous video that there's always an equal charge, but opposite magnitude on each side of the capacitor, which means that on this side of the capacitor it is equal to 8 microcoulombs, and on this side of the capacitor it's equal to negative 8 microcoulombs. It's attached to the negative side of the battery, so it's negative charge. Positive side of the battery is positive charge. We know that circuit 1, 2, and 3 are all the same circuit, but they are simplified. So let's take this system and let's apply it to the other capacitor systems. We know that at this point the charge is equal to 8 microcoulombs, and at this point it's equal to negative 8 microcoulombs. That's just what's right here. It's the charge on each end is equal to the simplified system. So we know that on each side of the capacitor, same magnitude of charge but opposite sign. Since this is 8 microcoulombs, this must be negative 8 microcoulombs. Since this is negative 8 microcoulombs, this must be 8 microcoulombs. So we solve that way. So now we know the charge on each of the capacitors. There's something else I should bring up. So Q equals CV. We know capacitance, we know voltage for this. And we also know that the voltage across the capacitor is 4 volts because all the voltage drop must be across the only component there. But this is interesting right here because here there are 2 components. So what do? There must be a voltage drop across this capacitor, and there must be a voltage drop across this capacitor. But what is it? We know that they must equal to 4 volts because that's the total voltage created. But let's solve it using this formula. We just solved that the charge here for the capacitor 1 is 8 microcoulombs. We know that the capacitor is 6 microfarads. So what is the voltage? Let's solve for it. Voltage 1 is equal to 1.3 volts. Okay. So we can solve for that way. So let's apply the charge to this system also. We know that the charge here must be negative 8 microcoulombs. Here must be negative 8 microcoulombs. But what's in between? We know that the charge on the 3 microfarad plate, which is the same as it was here, is 8 microfarads right here. We also know that the charge here is 8 microfarads. But now the charge must be separated along 2 different capacitors. Fortunately, in this situation, each capacitor has the same capacitance, so the charge is evenly distributed. So we have 4 microcoulombs here and 4 microcoulombs here, positive for each. So on the opposite side, it must be negative 4 microcoulombs. And that's how we solve for charge. Now we try to solve for voltage over here, but that wasn't prepared. So let's solve for the voltage across this capacitor. We're going to call that voltage 3. We know that charge equals capacitance times voltage. The charge across this capacitor is equal to 8 microcoulombs. The capacitance is equal to 3 microfarads. And what is the voltage? Solving for voltage gives us that the voltage across this capacitor is equal to 2.7 volts. See, for voltage 1 here, which I solved to be 1.3, that makes sense because the total voltage is 4. So 4 minus 2.7 is 1.3. So we have a 4 volt rise, a 1.3 volt drop, a 2.7 volt drop. This seems complicated now, the concept of voltage in a circuit, but in future videos we're going to talk about it.